Momentum seems like one of the simplest ideas in physics. If something is moving, it has momentum. If it moves faster, it has more momentum. If it has more mass, it has more momentum. And that gets compressed into one equation that almost everyone has seen before: P equals mv. And honestly, at first, there's nothing strange about that. It feels completely natural. It feels obvious. Almost too obvious to question. Momentum is just mass times velocity. End of story. But that equation hides an assumption so basic that we usually don't even notice it's there. It assumes that velocity is something an object always has in a clean, well defined way. It assumes that at any moment you can point to an object, know where it is, look at how its position is changing, and assign it a definite velocity. That works beautifully in classical physics. A baseball has a position, a car has a position, a planet has a position. They move along paths. If I know where they are now and where they are a moment later, I can talk about velocity. And once I have velocity, I can talk about momentum. But quantum mechanics starts with a very uncomfortable fact. Not everything behaves like a tiny baseball. Not everything behaves like a point like object following a clean trajectory through space. At very small scales, that classical picture starts to crack. And once it cracks, the usual idea of momentum starts to crack with it. Because now we have to ask a question that sounds simple but completely changes everything. What if a particle doesn't have a well defined velocity at all? That sounds absurd at first. How can something exist and not have a definite velocity? But that question only feels absurd because we're used to imagining particles as little objects flying around like dust. Quantum mechanics forces us to stop imagining that. It forces us to let go of the picture before it gives us a better one. At small scales, the best description of a particle is not, here it is moving with this speed. Instead, the description becomes spread out. The particle is not represented by a single point with a little arrow attached to it. It is represented by a wave function. And that word sounds intimidating, but for now, the important point is just this: the object is no longer being described as a little dot with a path. Instead, it is described by something extended in space, something that can be spread out, something that can interfere, and something that behaves much more like a wave than a classical particle. And once that happens, the old definition of momentum becomes suspicious. Because in classical mechanics, momentum depends on velocity, and velocity depends on tracking position over time. But if the object isn't localized in the first place, then what exactly are we tracking? What is the position of something that is fundamentally spread out? And if there is no sharply defined position, how can there be a sharply defined velocity in the classical sense? This is where quantum mechanics doesn't just modify classical physics, it replaces part of its language. Instead of asking, where is the particle and how fast is it moving, we start asking, what is the wave function doing? This is a huge shift. It means that if we want to recover momentum, we shouldn't be looking for little arrows attached to a particle. We should be looking for some features of the wave itself. Momentum must be encoded somewhere in the structure of the wave function. And that sounds strange, but there's actually a really beautiful clue that points us in the right direction. Waves have wavelength, and long before a full course in quantum mechanics, there's already a known connection between momentum and wavelength. Shorter wavelength means larger momentum, longer wavelength means smaller momentum. So, already, before we even talk about operators or derivatives, there's a hint that momentum is not really about motion in the classical sense anymore. It's about the spatial behavior of waves. A high momentum state corresponds to a wave that oscillates rapidly in space. A low momentum state corresponds to a wave that changes more slowly. So momentum is somehow tied to how quickly the wave varies as you move throughout space. And once you notice that, there's one mathematical tool that should immediately come to mind: the derivative. Because what does a derivative measure? Change. Specifically, change with respect to something. In this case, change with respect to position. So if momentum is tied to how rapidly the wave changes in space, then the derivative, with respect to position, is the natural place to look. This is the point where the math stops looking random and starts looking inevitable. Take a simple wave, something like an exponential oscillation, a wave of the form e to the ikx. This is one of the cleanest possible waves you can write down. It has a definite wavelength, and because of that, it corresponds to a definite momentum. Now, ask a question. What happens if we differentiate that wave with respect to x? When you do that, something very special happens. The derivative does not destroy the wave. It does not turn it into some completely different object. It gives you back the same wave multiplied by a constant factor, ik. And that matters because the wave stays essentially the same. The derivative is pulling out information from it. The wave is acting like a special kind of state, one where this derivative operation returns the same function times a number. That number is exactly the kind of thing we want. Because in quantum mechanics, states with definite measurable values often behave this way. You act on them with an operator, and you get the same state back multiplied by the value of the quantity you're measuring. So now, the puzzle starts to resolve. If differentiating the wave pulls out a factor involving k, and if momentum is proportional to k, then the derivative is directly connected to momentum, not metaphorically, literally. But we still need the constants to work out correctly. We need something with the right units, and we need it to match the known relation between momentum and wavelength. And when you include that constant factor, you get one of the most important expressions in quantum mechanics: the momentum operator, minus I h bar times the derivative with respect to x. That is the quantum mechanical definition of momentum. Momentum is no longer just mass times velocity. In quantum mechanics, momentum is not a simple number you assign by imagining a particle flying through space. It is an operation. It is something you do to the wave function. It is encoded in how the wave changes from one point in space to another. That is a much deeper idea than the classical one.
And this also explains why some waves have definite momentum while others do not. If you have a pure wave with a single wavelength, then it has a single value of k, which means a single momentum.
But most physically realistic states are not just one infinite perfect wave. They are a combination of many waves. And the moment you combine different wavelengths, you combine different momenta. So now the state no longer has one exact momentum, it has a spread of possible momentum values. And that leads to one of the deepest consequences of this whole framework. If you want a particle to be localized in space, you cannot describe it with one perfectly smooth infinite wave. A single wave extends everywhere. It is completely delocalized. So if you want to localize the particle, you need to build a wave packet. You need many different waves interfering together so that they cancel in some places and reinforce in others. That interference creates a localized bump, something that is much more particle-like in position space. But there's a price. The moment you use many waves, you are using many wavelengths, which means you are using many momenta. So the more localized the particle becomes in position, the less definite it becomes in momentum. The very thing that makes a state localized is the same thing that gives its momentum uncertainty. And now the uncertainty principle stops looking like some mysterious rule that dropped from outer space. It becomes a natural consequence of how waves worked. Position and momentum are linked because localization in one requires a spread in the other. And once you see momentum as a derivative, that starts to make intuitive sense. A sharply localized wave function changes rapidly. Rapid changes means the derivative will be large, and large derivatives mean strong momentum components. So a narrow position distribution naturally comes with broad momentum content. On the other hand, a perfectly smooth infinite wave has a single momentum. Its derivative behavior is completely regular, but then position is lost. There's no localized particle anymore, just a wave spread through all space. In quantum mechanics, momentum belongs to the spatial structure of a state. That is why the derivative appears, not because physicists wanted the math to be weird, but because the derivative is the natural mathematical tool for measuring how a wave varies in space. And that variation is exactly where momentum lives. And once you accept that, the rest of quantum mechanics starts to feel less like a list of strange formulas and more like a coherent new language. Because momentum is not the only thing that gets promoted from a number to an operator, energy does too. And that opens the door to one of the most important equations in all of physics, the Schrodinger equation. That is where all of this really comes together. Because once you know how momentum acts on a wave function, and once you know how energy acts on a wave function, you can start writing down the actual laws that govern how quantum systems evolve. So, if classical momentum was the beginning of the story, this operator version of momentum is the beginning of a much deeper one. Momentum isn't motion, it's not just mass times velocity. In quantum mechanics, momentum is how the wave changes in space. And that single shift in perspective changes everything. Thanks for watching. If you enjoyed this, subscribe, and I'll see you in the next one.